Welcome to the lesson on congruence of triangles. At the end of this lesson, you will be able to define the congruence of triangles and state the criteria for the congruence of two triangles. Let's discuss the congruence of triangles. Consider two triangles ABC and XYZ such that the corresponding angles are equal. And corresponding sides of both the triangles are equal. Here you see that the sides of triangle ABC coincide with the sides of triangle XYZ. The angles of triangle ABC cover the angles of triangle XYZ. So we can say that the triangles are congruent, and they are denoted by the symbol. Here, the tilde symbol represents that the triangles are the same in shape, and the equal symbol represents that the triangles are equal in size. In general, two triangles are congruent if all the sides and all the angles of one triangle are equal to the corresponding sides and angles of the other triangle. Here, triangle ABC is congruent to triangle XYZ. This also means A corresponds to X, B corresponds to Y, and C corresponds to Z. For any two congruent triangles, the corresponding parts are equal, and it is termed as the corresponding parts of a congruent triangle, or CPCT. Based on the above discussion, we conclude that triangle ABC is congruent to triangle XYZ. But triangle ABC is not congruent to triangle YZX. Congruence of two triangles is defined based on different criteria. We know that two triangles are congruent if all the 6 parts of one triangle are equal to the corresponding 6 parts of the other triangle. You can also prove two triangles are congruent even if the 3 parts of one triangle is equal to the corresponding parts of the other triangle. We'll discuss the basic 4 criteria that state two triangles are congruent. Let's begin with the side-angle-side congruence rule. Two triangles are congruent if two sides and the included angle of one triangle are equal to the corresponding 2 sides and the included angle of the other triangle. This criterion is referred to as the side-angle-side or SAS congruence rule. Consider triangles ABC and XYZ such that side AB is equal to side XY, side BC is equal to side YZ, and angle B is equal to angle Y. Then triangle ABC is congruent to triangle XYZ. It is true for the congruent triangles if their corresponding 2 sides and the included angles are equal. It is considered to be an axiom. Next, the second congruence rule states that two triangles are congruent if 2 angles and the included side of one triangle are equal to the 2 angles and the included side of the other triangle. This is referred to as the angle-side angle or ASA congruence rule. Let's prove it. Consider two triangles ABC and XYZ such that angle B is equal to angle Y, angle C is equal to angle Z, and BC is equal to YZ. To prove these triangles are congruent, we use the SAS congruence rule. In this situation, you may encounter three cases. AB is equal to XY, AB is greater than XY, and AB is lesser than XY. Let's start with case 1, where AB is equal to XY. In triangles ABC and XYZ, you see AB is equal to XY, angle B is equal to angle Y, and BC is equal to YZ. This data satisfies the SAS congruence rule. Therefore, triangle ABC is congruent to triangle XYZ. In the second case, let's assume that AB is greater than XY. Consider a point P on AB such that BP is equal to XY. Now, in triangles PBC and XYZ, PB is equal to XY, angle B is equal to angle Y, and BC is equal to YZ. Thus, by SAS axiom, triangle PBC is congruent to triangle XYZ. Since corresponding parts of congruent triangles are equal, thus angle PCB is equal to angle XZY. We are given that angle ACB is equal to angle XZY. So, angle ACB is equal to angle PCB. This is possible only if P coincides with A. So AB is equal to PB. But we have assumed that PB is equal to XY. This implies that AB is equal to XY. Also, angle B is equal to angle Y, and BC is equal to YZ. Therefore, by the SAS congruence rule, triangle ABC is congruent to triangle XYZ. Lastly, consider AB is less than XY. In this case, consider a point Q on XY such that QY is equal to AB. Proceeding the same way as we did in case 2, we can conclude that QY is equal to XY. Therefore, by the SAS congruence rule, triangle ABC is congruent to triangle XYZ. We know that the sum of the three angles of a triangle is 180 degrees. If two angles of one triangle are equal to the corresponding two angles of another triangle, then the third angles of both the triangles will also be equal. Thus, instead of the included side, we may have any pair of corresponding sides equal. Thus, the ASA congruence rule is sometimes referred as AAS or SAA congruence rule. Since this result has been proved, it is considered a theorem. Two triangles are congruent if three sides of one triangle are equal to three sides of another triangle. This is referred to as the side-side-side or SSS congruence rule. This can only be proved by construction. Consider a triangle ABC. We'll now construct triangle XYZ by using the sides of triangle ABC. On comparing, we see that the respective sides are equal. Therefore, the triangles are congruent. Two right-angled triangles are congruent if the hypotenuse and a side of one triangle are equal to the hypotenuse and the corresponding side of the other triangle. This is referred to as the right-angled hypotenuse side or RHS congruence rule. This rule is applicable only for the right-angled triangles, while the rules studied so far are applicable for any triangles. As you've seen, we say two triangles are congruent if at least three parts of one triangle are equal to the corresponding three parts of the other triangle. But this is not always true. For example, side-side angle or SSA. angle side-side or ASS and angle-angle-angle or AAA are not sufficient to prove the congruence of two triangles. Let's look at some examples to understand it better. Consider two triangles ABC and XYZ, where AB is equal to XY, BC is equal to YZ, and angle C is equal to angle X. Can you superimpose these triangles? This is not possible. Hence, the triangles are not congruent. Therefore, side-side angle criterion does not hold true. Now, let's take an example to examine AAA criteria. Let's look at the triangles. In these, the corresponding angles are equal. Here, the sides of one triangle are not equal to the sides of the other triangle. Therefore, these triangles are not congruent. Let's recap. Two triangles are congruent if the sides and angles of one triangle are equal to the corresponding sides and angles of the other triangle. There is a 1-to-1 correspondence between the vertices of two congruent triangles, ABC and XYZ, such that A corresponds to X, B to Y, and C to Z. Two triangles are congruent if two sides and the included angle of one triangle are equal to the corresponding two sides and the included angle of the other triangle. It is referred as side-angle-side or SAS congruence rule. Two triangles are congruent if two angles and the included side of one triangle are equal to the two angles and the included side of the other triangle. It is referred as angle-side-angle or ASA congruence rule. Two triangles are congruent if three sides of one triangle are equal to three sides of the other triangle. This is referred as side-side-side or SSS congruence rule. Two right-angled triangles are congruent if the hypotenuse and a side of one triangle are equal to the hypotenuse and the corresponding side of the other triangle. This is referred as right-angle hypotenuse side or RHS congruence rule. Welcome to the lesson on properties of a triangle. At the end of this lesson, you will be able to prove that angles opposite to equal sides of an isosceles triangle are equal, and that sides opposite to equal angles of a triangle are equal. You will also be able to solve problems based on the properties of an isosceles triangle. Consider this triangle. Can you determine its type? On measuring its sides, we can see that two of its sides are equal. It's an isosceles triangle. The third side becomes the base of the isosceles triangle. Now, let's join the vertex to the base of the triangle. If we fold the triangle along this line, it divides the triangle into two equal right-angled triangles. As you can see, the corresponding sides and angles of these two triangles are equal. Coming back to the isosceles triangle, we have two equal sides and the angles opposite to these sides are also equal. Based on these observations, we can conclude that angles opposite to the equal sides of an isosceles triangle are equal. We will prove it by using the criteria of congruence. Consider two triangles. For these triangles to be congruent, the sides and the angles of one triangle must be equal to the corresponding sides and angles of the other. Congruency of triangles can be proved using the four criteria of congruence: SAS congruence rule, ASA or AAS or SAA congruence rule, SSS congruence rule, and RHS congruence rule. Using some of these criteria, we will prove two important theorems of an isosceles triangle. To prove that angles opposite to equal sides of an isosceles triangle are equal, we'll consider an isosceles triangle ABC. Here, side AB is equal to side AC. We have to prove that angle B is equal to angle C. Angle B is opposite to side AC, and angle C is opposite to side AB. We'll begin by drawing a bisector of angle BAC meeting BC at D. First, we will show that triangle ABD is congruent to triangle ACD. In triangle ABD and triangle ACD, side AB is equal to side AC. This is because triangle ABC is isosceles. Angle BAD is equal to angle CAD, since AD is a bisector of angle A. Side AD is common to both the triangles. Now, by SAS axiom, if two sides and the included angle of one triangle are equal to the two sides and the included angle of the other triangle, then the triangles are congruent. Thus, triangle ABD congruent to triangle ACD. And since the corresponding parts of the congruent triangles are equal, therefore, angle B is equal to angle C. This was simple, wasn't it? The converse of the above theorem is also true. Let's try proving it. The sides opposite to equal angles of a triangle are equal. Let ABC be the given triangle in which angle B is equal to angle C. Using this information, we'll prove that side AB is equal to side AC, which are the sides opposite to the equal angles. Like we did in the previous proof, here too, we'll draw a bisector from the vertex to the base. This divides the triangle into two triangles. After that, using the criteria of congruence, we'll prove that the resulting two triangles are congruent. Then using CPCT, which implies that corresponding sides are equal, we'll prove the converse theorem. Let's draw bisector AD of angle BAC meeting BC at D. Thus, two triangles ABD and ACD are obtained. In triangle ABD and triangle ACD, we are given that angle B is equal to angle C. Angle BAD is equal to angle CAD, since AD is bisector of angle A, and side AD is common to both the triangles. Now, as we know, by the AAS criterion, if two angles and one side of one triangle equals two angles and one side of the other triangle, then the two triangles are congruent. Thus, triangle ABD is congruent to triangle ACD. And since corresponding parts of congruent triangles are equal, side AB is equal to side AC. Welcome to the lesson on inequalities in a triangle. At the end of the lesson, you should be able to identify the theorems on inequalities of a triangle and apply the theorem to solve problems involving inequalities of triangles. A triangle has three sides. Three angles are included by the three sides. If we replace one side with a longer side, the measure of the three angles change. This says that the angles and the lengths of the sides are proportional. Let's perform an activity to understand this. Let's take three sticks of length 6, 8, and 10 units respectively. We arrange the sticks to form a triangle. What type of a triangle is this? It's a right angle triangle. Let's name the triangle as ABC. Observe the triangle and its angles. The angles measure 90 degrees, 37 degrees, and 53 degrees. Let's experiment using this triangle. The 10-unit stick is replaced with 11-unit stick. Observe angle B. Let's repeat the experiment for a 12-unit stick and a 13-unit stick. What can we observe here? As we keep on increasing the length of the stick, the angle opposite to the stick increases proportionately. Now let's have a recap. So can we say that the measure of the angle varies according to the side opposite to it? By using the observation, we shall verify two theorems. The first theorem says that if two sides of a triangle are unequal, the angle opposite to the longer side is larger. To understand this theorem, let's use the first triangle. For example, let's consider the 10-unit, 8 units, and 6 unit sticks in the first triangle. Of these, the 10-unit stick is of greater length. Now compare the angles opposite to the 10-unit stick and the 8-unit stick. You can observe that the angle opposite to the 10-unit stick is greater. Likewise, you can verify the angles opposite to the 8 and 6-unit sticks. As an exercise, you can verify other triangles also. Now, let's verify the second theorem. The theorem says that in any triangle, the side opposite to the larger angle is longer. Now, let's verify this theorem using the first triangle. The greatest angle in this triangle is 90 degrees. You can verify that the side opposite to the greatest angle is the 10-unit stick, which is the longest stick among the three sticks. As an exercise, you can verify this with other triangles also. The second theorem is converse of the first theorem. Now, let's learn about the other theorem. This theorem is about the sum of sides of the triangle. The theorem says that the sum of any two sides of a triangle is greater than the third side. To verify it, let's take a triangle with sides A, B, and C. Of the three sides, if we take any two sides at a time, the sum of the two sides is greater than the third side. That is, let's verify this through an activity. We will use the same example we have used for the other theorems. Let's substitute the sides A, B and C with 6, 8 and 10 respectively. If we consider two sticks at a time and add their lengths, we observe the following. Now let's try to construct a triangle with the sticks of length 6, 8 and 14 units. Is it possible to construct a triangle with these sides? You can observe that it is impossible to form a triangle. Let's see why. On comparing, we find that the sum of the two sides is equal to the third side. We cannot construct a triangle with such measurements. Similarly, we cannot construct a triangle if the sum of the two sides is less than the third side.